Hi guys, welcome to Geeks for Geeks practice. So today we are going to see another question that was asked yesterday in problem of the day. Yeah, hi Utkarsh. Thank you for such kind comments. Okay, so let me read it. Okay, it's really, thank you. It's really a great initiative by Geeks for Geeks to start with problem of the day. Okay, that's really nice that we are able to help you. Thank you, Utkarsh. From couple of days, it is seen that problem of the day is more focused towards trees and graphs, and specifically to me, I'm not good at it. It's okay. It's okay. So you can also start DSSAs. Okay, Utkarsh. So our team will look at this. Okay, and we'll let you know. Okay, great. Yeah. Hi, Milan. Okay, guys. So let me share my screen. Let's start with today's lesson. Okay. So just a second. Yeah. Sorry for that 1 2 minutes delay. Okay. Yeah. Good evening, Karthik. Just a second. So data science lingo is saying, hi Rohit, can I send my code if you can see where I'm doing wrong? Sure, sure. You can comment. You can send the code in comments. Okay. Yeah. Hi Vidya. Thank you guys. Thank you for joining. So just confirm is that my screen is visible or not. Okay. I'm sharing my screen. All right. So yeah, let's go to the problem of the day. Okay. Yeah, guys. And before going to the problem of the day, I would like to focus some attention over here on our live and online courses. Okay, so you can do check them out once, and if it's applicable or if it's good for you, you can go with it. Okay. So let's go to the problem of the day that was asked yesterday. Okay, so the question of yesterday is this one. All right. So as you guys must be aware of, right, that I usually take the description of the question on whiteboard. So let's go over there and let's try to understand this question. Okay. We'll come to Geeks for Geeks practice portal once we are done with the logic and approach. Right. Great. So guys, I just wanted to share one thing with all of you. Like in my lessons, whenever I discuss the question and the approach, okay, and after that when I show the code. So from your end, do give a try to implement it yourself, maybe through some other logic or the same logic. See why I am saying this, because in few of the problems which are very big, most of the time is going on in going through the logic, answering the cross questions of most of you and describing the question, right? So I am not getting full time to do a dry run. Okay. But if you have any comments, you can surely comment it down. I'll reply it back. You can go and check the comments on the last lesson, that is burning tree question. Okay. And before that, minimum cost of ropes. Right. Okay. Because I have basically pointed out few things which was not pointed due to lack of time. Okay. But it's okay. If you have any doubt, you can let me know in the comments. Great. So today let's go with the means yesterday's problem of the day. So the question says that we need to remove BST keys outside given range. Okay. So first of all, we need to understand what is a BST, right? Great. So BST is a binary search tree. All right. So what's special about it? So it is a node-based binary tree, but it has few properties. Okay, we'll look at that. So as Utkarsh said that a lot of questions are coming on trees and graphs. Okay, so it's okay. Like eventually we will see that things will get distributed. Okay, I guess. Okay, let's begin. So let me take an example. Let's take this example. Okay, this is a binary search tree. So what happens is, see, first of all, in binary search tree also we will have at most two nodes, okay? Because it is a binary tree, but with some extra constraints. So extra constraints is, let's say you take this key, okay, 6. Now anything to the left of 6, okay, will be smaller than 6, exactly smaller, okay, exactly smaller. I'm not even saying like you will get duplicate elements, because binary search tree has distinct elements present in it, okay? And if you take the right of 6, all of the elements are greater than 6. Okay. Now, let's try to understand it in more detail. Basically, this particular less than, greater than on left and right side of nodes is applicable for each and every node. Okay. So if you now look at, let's say, 14. So what you're going to observe is, on the right of 14, I have all the nodes greater than 14. And on the left of 14, I have all the nodes which are smaller than or less than 14. Right. This is the exact property for all of them. If you take 13, see, in left we have 7, which is smaller. In right there is nothing, it's null, right? Now if you take this node minus 13, in right we have minus 8, which is greater than minus 13. In left we have nothing, it's null, right? So yeah, for 13 also, in left you have 7, which is less than 13, and in right you have nothing. Okay. So these are the three properties. The left subtree of a node contains only nodes with keys later than the node's key. That's true. The right subtree of the node contains only nodes with keys greater than the node's key. The left and right subtree each must also be a binary search tree. That's what I showed to you, right? Like for 6, see, this is its left subtree and this is its right subtree. Now this in itself is a binary search tree. Now this in itself is a binary search tree, right? The two subtrees also are binary search trees. Okay. So I hope the definition of binary search tree is clear to all of you. Okay, guys. So if this is clear, now let's come to the question. Okay, what it's saying. And if you have any doubts regarding binary search tree definition or how it looks like, you can let me know in comments. Okay. Okay. Yeah. Great. Great. Thank you, guys, for the confirmation. Thank you, Aditya. So yeah. Thanks, Aditya. Yeah. So we have given a binary search tree. Okay, that's great, Karthik. We have been given a binary search tree and a range, min and max. Okay, fine. So this is your binary search tree and this is your range, right? Like it's inclusive. Okay, the range is also inclusive. So we'll look. We need to remove all the keys which are outside the given range. So what it means is, if you have a look at it over here, how many nodes are outside? Like 6 is inside this range, right? Minus 13 is outside this range, so we need to remove it. Okay. And after that, what else we have outside the range? 14 is outside the range, 15 is outside the range, right? Minus 8 is in range, 13 is exactly equal to this, so it's also in range. That's what I said. You need to consider equality over here. Okay. You need to include them. So 13 is exactly in range, so that's the reason we are not going to remove it. 7 is anyways between the two. Okay. So basically you need to remove all these nodes and you need to finally return the elements which are like in the range. Okay. You need to remove all the elements that are outside the range. And please note that you need to consider, if minus 10 is there in the tree, you should not remove it. If 13 is there in the tree, you should not remove it. You should only remove all the keys that are outside the range. Okay. Great. So if this is clear, let's try to understand how we can go with the approach. Okay. So let me just clear the screen for now. Okay, because now I'm going to discuss the approach. Okay. So we need to remove minus 13, 14, and 15. Great. Fine. So let me just clear the screen. Okay, let this question be over here. No issue. Yeah, let it be. See, let me redraw the tree. Okay. 6 minus 13, 14 minus 8 13, 15, and 7, right? Okay. Okay, first of all, what comes in my mind is let's decide how to traverse the tree. Okay, because you need to remove elements from it, right? So it depends. Like if you need to remove something from the tree, you need to go through those nodes at least, right? This is the first basic thing which I'm saying. Like I'm just trying to develop the thought process. So let's try to decide what should be the traversal. Okay, how we need to traverse the tree. Okay. So we can traverse the tree in three fashion, right? Like it could be pre-order traversal, in-order traversal, or post-order traversal, right? So let me write it down. We can either travel in pre-order, in order, or in post-order, right? So in post-order, what we do, we travel first the left, right, and after that we travel the route. In order, we go with left, then route, then right. In pre-order, we go with route, then left, then right. So we need to decide what way we need to traverse. Okay, then only we can think of removing the elements. Okay, so I'll explain it to you like why we need to choose one out of the rest. Okay, let me have a look at the comments once. So Karthik is saying, sir, can we use rotation, LL, and RR and remove it? Okay, so Karthik, are you talking about balancing in AVL tree concepts? See, we should not make a simple question complex, to be honest with you. Okay. Like you can give a try, but I don't think it will work for all the test cases. Okay. So let's have a look at it. Okay. I'll take more questions if time is there at the end. Okay. All right. Great, great. So Milind is saying, I think to do in order as BST is also sorted. Okay. Okay. Let's have a look at it, Milind. Okay. So this is my tree, right? Now let's first assume that we are going to take post order. Okay, let's first assume. So what's going to happen if I go with post order traversal? I am over here, right? I am at 6. Let me create some space. Yeah, I am at 6, right? Now what I have done, okay, or just a second. Yeah, fine. I am at 6. Now post order says that left, right, then root, right? So basically the calls will be, if I go, it will be first call will be root dot left. Okay, like let's say my function name is traverse or something, then the call will be for root dot right. After that, over here I'm going to do the operations on root, right? Basically I'm going to take things, do some operations on root dot data. We'll be checking whether it's lying in the range or outside the range, right? Okay, fine. So let's first go with post order. Let's see if we can reject this. Okay, fine. So we are here with 6. Okay, we go to the left. Again, we go to the left. We find a null, right? So we return. Fine, we returned. Now we call on its right. We see a -8, right? Again, we call on its left. We see a null. We return. Over here, we see a null in right and we return. So now we are somewhere, we have the data root dot data 8, right? I have traversed whole left and right of root node, basically current root 8, and now I can do some operation on this. Sorry, this is -8, right? Sorry guys, so I am over here at -8, right? So now I can check whether this -8 is in range or outside range, right? Okay, so -8 lies somewhere over here, right? It's in range, so I don't need to do anything, right? Suppose it was -11. Okay, suppose it was -11. Let me create some space. Okay, things are becoming clumsy. Suppose in place of 8, I had -11. Okay. Then what I need to do? Then obviously I need to remove it, right? Because the question says remove BST keys outside given range. So -11 lies outside. It is lesser than -10, right? I need to remove it. Great. So I can remove it. What I can do is I can just make it to null. Okay. Okay. Or let me come up with the logic. Okay. What I should exactly do. Let's try to utilize the feature of BST. So if it is minus 11, can I say that all to the left of minus 11 will be less than that? And all to the right of minus 11 will be greater than that. So if minus 11 is already less than my least value, that is minus 10, can I say all of the left hand side is going to be worthless? Those are going to be more lesser. Can I say this? Okay, guys, if this is clear, okay, if this is clear, okay. So yeah, great. So I can remove all of this, right? Because I know that minus 11 is out of range. Obviously, all of this will also be out of range. So what I can do is I can straight away assign to minus 13 whatever is there on the right of 11. Okay, basically, how it's going to become, I'm going to return root dot right. Basically, I'm going to return minus 11 dot right. Right now it's null. Right now it's null, but what if it had some subtree? Okay, so I can return root dot right, and this minus 11 goes out of picture, and I have null right now because anyways I did not had anything to the right of minus 11. But if it would add something, I would have got it, right? I would have got it properly. Fine. So now I have reached to minus 13. Great. So I have reached to minus 13. By mistake, I erased the 7 also. Okay. So guys, please do let me know in comments, okay, if I do such erase, because when I was doing this size of eraser was, I guess, big. Okay. No issues. Okay. Great. So now we are at minus 13. How? We are at minus 13 because we have seen all the left and right of 13, and that's how post order traversal goes. Again, we check for minus 13. Right. So minus 13 is C, minus 13 is again outside. Okay, guys, how many of you noticed that minus, if even if I put minus 11, this is the correct BST? Because see, minus 11 is greater than minus 13 and 6 is greater than minus 11, right? So we can have minus 11, okay? Okay, fine. Now let's come back to our recent iteration. So we see minus 13 over here, great. And we find that it's again now out of range. So same logic goes. Minus 13, anything to the left of it, again is going to be more smaller. I can simply return right. Right now it has null, so no issues. I'll have null, right? So if this is fine, now we are done with left subtree of 6. We are going to traverse right subtree. So we are going to do things in similar fashion, okay? Fine. Now let's. So things are going to happen properly in post order. Like if you want to know, then let me do it. Okay, let me complete this pottery because it will take some time. So just I just wanted to go to another traversal, but it's fine. Let's go. So we are over here, right? This 14 again calls to its left, that is 13. Then 13 again calls to its left, that is 7. See, guys, for those of you who, for whom things are not crystal clear right now, don't worry, we will see the pseudocode for this, okay? Okay, and yeah, for people who are able to follow, that's great. And for those of you who are not able to follow exactly right now, please comment, okay, so that I can explain it. Anyways, things are going to become crystal clear when we see the pseudocode, okay? Great. So we now go from 14 to 13, 13 to 7, and the same thing. What we see over here is 7's left is null. Okay, so fine. We are going to return. That is going to be the base case. We will see. 7's right is also null. So we have completed left and right subtree of 7. We are going to check this 7, right? So 7 is lying inside it. No, nothing. No need to do anything. Go back. Okay, so left subtree of 13 is completed. I come to right subtree, that is null. So right subtree of 13 is also completed. I can now check with 13. So is 13 lying in the range? Yeah, it's exactly equal. So we need to let it be there. Okay, we don't need to remove it. Great. So now left subtree of 14 is completed, right? Let's go to the right subtree of 14. Okay, now comes the interesting part. When we go to the right subtree of 14, we find 15, right? 15 again calls on its left, which is null. 15 calls on its right, which is null. 15 is checked, which is lying greater than 13. So we need to remove it. Now comes the important observation. If I have 15, okay, if I have 15, then what's going to happen? I know that in the right of 15, everything will be greater than 15, right? And in the left of 15, things will be smaller than 15. So if 15 is already greater than 13, can I say I can get rid of this right part? Like, this is not required because all of them will be greater than 13, right? So is this clear, guys? How we are trying to utilize the logic of binary search tree? So that's what we are going to do. Although it is not making much sense over here because to the right of 15 we have null. Okay, but you will eventually see. Okay, where it will make sense. Okay, great, great guys that you people are following. I see a comment from Aditya. I guess the LST of root 6 should have -8. Uh, yeah, it should have, Aditya. Maybe it got removed while I was erasing. Okay, don't worry, we will see a dry run at the end. Okay, basically what I was doing over here, I changed this -8 to -11, and I was trying to show you what's going to happen with -11, right? So that's the reason I removed -8. So I am not going with this input exactly. So I hope you get it right, Aditya. Like I changed it to -11 if you remember, just to make you understand the logic when we are going to discard which part of the tree, right? Okay, great guys. So if this is clear, yeah, okay, great, Aditya. So if this is clear, let's proceed. Okay, fine. So we are going to return. What we are going to return? We are going to return left half of the tree because 15's right half is useless to me. I know anyways those all will be bigger than 15, right? So I'm going to return this left half of the tree. That's great. Okay, so I have one more condition to return root dot left. Okay, we'll see in the pseudocode. We'll see where we are going to write all this. Okay, don't worry. I'm just writing all of them right now very haphazardly here and there, but it's fine. I hope all of you are able to follow. Right? Great. So now we are returning from here root dot left. So basically, I'm going to return null. Fine. And where it's going to be returned? It's going to be returned to the call of 14 dot right. Right, to the call of 14 dot right. So when I write the pseudocode, you will be seeing that I am writing something like this. Root dot left equals to traverse root dot left and root dot right equals to traverse root dot right because I need to keep on replacing stuffs, right? Okay. Okay. So just a second. Still there is a catch. Uh, we saw 15, right? 15 was greater. So we returned null from there, right? Okay. Just a second. Yeah. So for 14, right, we are going to return a null and this 15 is going to vanish, right? Great. Now the subtree call for both 14 left subtree and right subtree is finished, right? If this is done, we are again going to check for this 14. See, this is interesting. Till now, we were seeing those nodes where our subtrees were mostly null, okay? But this 14 has a left subtree now. So there comes the important part. This 14, for 14, can I say again, as it is greater than 13, this right subtree is not going to play any role. This left subtree is important because in right, anyways, all the values will be greater than 14, right? So I can simply return root dot left. So where will this get returned? This will get returned to the 6 right because see how 14 got called. 14 got called from 6 right. So basically this 14 will be erased and root dot left. Basically 14 dot left now will be merged over here. So is this clear, guys? So we are left with 6, 13, and 7. And guys, this is not the same input. Okay, this -8 was taken as -11. Okay, so we removed -13, we removed -11, we removed 14, we removed 15. We are left with 6, 13, and 7. Right. So guys, is it making sense? Now see, as Utkarsh was saying, I guess Utkarsh only, right, or someone from the audience. Okay, Milind was saying, I guess. I think to do it in order. So Milind, now are you able to understand what wrong things will go if you do in order, or like, or if you want, we can see that. See what's going to happen. See, try to understand what's happening over here. First of all, we are correcting all the left and right, basically all its child. Then we are moving forward. But what happens in case of in order? Okay, what happens in case of in order? You first see your left, then you go and correct your 13. Now see where will be the error. I'll show it to you. Okay, let's say in place of -8, I had -11. Okay, I'm just giving a very brief of in order approach. Okay. If you guys need it in detail, let me know. Or if time is left at the end, I'll surely show. Okay. See, if this -11 you get and you're doing an in order, okay. So what's going to happen? You will see the left of this, then you will straight away go to this. Now, when you go to this -13, right? So -13 is less than -10, right? So obviously anything to the left of it is not going to make sense. All will be more or less. You are straight away going to return this right. So if you do that, see what you're doing. If you are returning this tree which has -11 in it, okay, -8 is let's say not there. That's wrong because -11 is also outside range, right? So guys, I hope the in order approach is clear and as well as the post order approach is clear, right? And we will have a look at the pre-order approach when we go to the implementation of the implementation of the code on Geeks for Geeks practice portal. Okay. So guys, do you have any doubts till now? Can I write the pseudo code for this now? Like, anyways, most of the code is on the screen, but I'll just organize them. Okay. Great guys. As I see, there are no more questions. Let's go with the pseudo code. See, for those of you who have difficulty in trees, okay, let me give you a tip, okay, a very efficient tip. Whenever you are solving questions on trees, okay, realize or I would say visualize things in terms of only three nodes, okay. Now these three nodes could be generalized in the sense this could entire be a tree. Okay, I am not bothered as of now. I am visualizing all of them as if I am just bothered till this point. Okay, like I am just focusing on my immediate left and right childs. Okay, to be more precise, focus on your immediate left and right childs, and rest recursion will do it for you. Okay, so I will not say exactly that. Go with like if you have multiple more nodes below it, I would not say exactly that realize all of them as only three nodes. Okay, I take that words back, really sorry for that, because that might also confuse you. Okay, what you can do is you can realize them as only your single node parent, your left child, your right child, rest, but that's it. Now you don't need to bother, you need to write your recursive function. Okay, and rest of the nodes will behave accordingly because they have somewhere the same data structure, right? This will help you because it helped me actually. Okay, it helped me solve really complex problems. So I guess this will help you. Okay, so after writing the code, then you can do a dry run. Okay, it at least it increase my efficiency. Okay, means I used to get confused at times. So what you can do is you can just visualize them as single parent, single left child, single right child, write your code, and then when your code is written, try to dry run on a test case. Okay, it might be means your code might be fully correct, might be wrong, but at least you will be able to think some better logic. Okay, I guess so you can give a try like that. Okay, so Karthik is saying, sir, how to calculate time complexity concept. So Karthik, do you is the question somewhere related to how to exactly means? See, in this case, we do single traversal. Okay, so the time complexity is anyways big often. So where n is the number of nodes. But if you want to go into the mathematics of time complexity, okay, if you go into the mathematics of time complexity, we need to have some separate lesson. Okay, where I need to show you for different kind of code structures how to calculate time complexity. Okay, and what are the various methods to calculate time complexity. Okay, yeah. So Vidya is saying, yeah, visualizing as three nodes will be helpful. Yeah, you can do that. Okay, I'm not saying that it will be always giving you the correct solution, but it might give you a head start. Okay, means it might help you. Okay, yeah, great. So, and yeah, if you do really well, then you might eventually land to correct solution also. Okay. Great. Fine. So now let's come back to the pseudocode, guys. Okay. Great. So what I was saying is, let's say I have a function. Let's say the function name is remove. Basically, I saw a few comments that was for having problem in trees and graphs. That's the reason I shared this tip. Okay, because this helped me somewhere. Okay, I guess. Okay. So what am I passing? Okay, let's say I'm passing the node root. After that, I'm passing, let's say, the minimum. Let's call it as L or low, or left. Let's say left of this range, and let's say call R or right of this range. Okay, great. Okay, guys. So if you just zoom this out a bit, I need some space. Okay. So initially, as you must have observed, like what we were doing, if we are getting null, we are simply returning. So if root is null, you can return root, you can return null, whatever you want, because root is itself null, right? Great. Now I'll do two calls for that post order. Okay. So let me call remove on root dot left, and I'll be storing it on root dot left only. I hope I was able to make this thing also clear, because you need to reassign stuffs, right? Right. Okay, so I need some more space. Great. Now, basically, if you have come to this part of your code, you know that you have visited the left and right halves, right? Okay. So now you need to operate on the data. Great. So if, sorry, it's root, right? So if root dot data is less than L, okay? So what I'm saying is, if my root dot data is lower than this, so if this is lower, I know that all the things to the left of it will all will be lower, right? That's a property of binary search tree. So what I need to return? I need to simply return root dot right. Okay. Is this making sense, guys? And there will be one more case if root dot data is greater than R. So I'm saying that it is beyond this. Okay. See, I'm not using equals to. I hope you get it right. Why I'm not using equals to? Because this 10 and 13 should not be removed. Right? Means sorry, this minus 10 and 13 should not be removed if it's there in the tree. Right? Why didn't, okay, Vidya is saying why didn't pass root as parameter? Okay, first of all, guys, I have made a small, see, anyways, it's a pseudo code, but yeah, this is how you need to pass it. Okay, now let me come to the question. Okay, so this was a small mistake, but I hope these things becomes clear when I go to the practice portal, right? Because more important is this post audit traversal, right? Okay, so let me come to the question. Why didn't pass root as parameter in root arrow left and root arrow right? Okay, so Vidya, are you asking about this? Why am I not passing root over here? Is that your question? Okay, okay, you get it right. Why I am not passing, or do I need to explain? Okay, if you need any further clarifications, do let me know. Okay, basically this is how we did the dry run, right? We, if you remember, what we did, we tried post order traversal. So in post order traversal, what we do, we go to the left, we complete all the left, we complete all the right, then we come back here, right? So if you observe, we go to left. Basically, this is a recursive call, right? It again goes back, comes back, goes back, comes back until unless it hits this base case. So it will hit the base case over here. Now it goes to the right of this node, right of this node. Then when these two are finished, I am operating on this, right? So this is how I was getting. So even if it is not clear, okay, do let me know in comments. I will explain it. Okay, no issue. I'll explain it once again. Great guys. So if things are clear till now, if root dot data is greater than right, so what I need to do? I need to simply get rid of all the right part, because what I'm saying is, uh, I know that if this is itself greater than my maximum means this range over here, obviously I don't need all of this because all of this will also be greater. So I'm going to return root dot left. Okay. And if these two are not true, then what you're going to do? You're going to do nothing. You're just going to return the root. That's it. Okay, as simple as that. So guys, is the pseudocode clear? Okay, if it's fine, now let's go to our practice portal of Geeks for Geeks. Okay, fine. So see, there is nothing new as such, but as I was doing the code, so what I found out is, just a second. As I was doing the code, so what I found is that this is inefficient. Inefficient in the sense, anyways, I am overwriting stuffs. Okay, so this is not required. So what I can do is, means as I showed you in the pseudocode, what we can do is we can simply return root dot right and root dot left. Okay, similarly over here, no need to create a new node and do all those stuff, because anyways you are overwriting things, right? Great. So now let's run it once, because see, anyways, I've explained the code. I have some extent showed you the in logic also how we are going to traverse and all those stuff. But we will see a dry run for this. Okay, no issue, because today we have time. Okay, so let me. Okay, let's first do a dry run. Okay, let's see what happens. Let's do a dry run for the same. Okay, so I need this as well, right? Okay, so let me draw it. Just a second. Or let's compile it once. Okay, after that we'll do a dry run. Okay, so data science lingo is saying, can you check my pseudocode? Yeah, sure, sure. I'll check after the live lesson. Okay, no issues in that. Okay, there is some server issue, I guess. Let's try to compile it once again. Okay, so we are getting this as output. Let's try to submit it. Okay, so it's giving correct answer. Now, guys, before going to the exact dry run, let's try to do in order traversal. Okay, in order traversal, anyways, it's seen that it was giving wrong answer. But if you want to visualize, okay, see, this is in order, right? I'm going first left, then I'm doing all the data on the root, then I'm doing the things on the right. So if you submit it, obviously you'll get a wrong answer. But let's see that. Okay, so it's giving a wrong answer. Fine. Let's have a look at pre-order also. Okay, so pre-order, what does it mean? That I'm going to do both of these checks before my call on left and right. Okay, so let's submit that as well. So this is also giving me a wrong answer. Why? You must have understood. Because if you take that example, you need to make sure that everything from the bottom is corrected. Because what you are doing, you are giving your left and right, root left, root right accordingly. So you need to ensure that your root left and root right is properly clear, right? Okay, so Vidya is asking why we will get wrong answer with pre and in order traversals. Okay, Vidya, I'll explain it to you. Okay, or like if you want, you can go back to the video. I have already shown why in order was giving wrong answer, but let's have a look at it once again. No issues. Let me correct this code. Right. So now let's submit it. Okay, guys, so this is giving correct answer. So post order is the correct approach. Now let me try to answer the queries. Okay, fine. So let's see exactly as Vidya is asking why in order and post order is not going to work. Okay, so let me write it down. Sorry, in order and pre order is not going to work. So let me choose the color, or let's go on the whiteboard itself. There things will be better. Fine. So let's say this is the tree. Okay, and I'm trying to do just a second. Let's say this is the tree, and what I'm trying to do, I'm trying to first go with in order traversal, suppose. Okay, great. So see what's going to happen in order traversal. In order, what happens? First we go to left, then we do operations on root, then we go to right. This is how in order works, right? So you go to 13, right? After that, okay, in order to explain it, just a second. Let's say in place of -8, I had 11, minus 11 over here, okay? And I am talking in terms of this right now. Let's say my root is 13. So what's going to happen if I'm going to do in order traversal? Okay, so let's see that. Or if you want, let's go from the beginning. Let this be -11. So initially I have 6. I go to left. 13. I go to left. I find the null. I return. Right. Now left of 13 is completed. I need to process this. Sorry, I'm again and again saying 13. It's -13. Okay. So left of -13 is completed. I need to process this now, right? That is how in order works. So if you process it, what's going to happen? See, you are going to check for that, right? If root dot data is less than L, then basically this. If root dot data is less than L, okay, this was one condition, and there was one more condition. So if this root dot data is less than L, what we were doing? This was the root, right? Let's say this is the root and it has two trees. Okay, so root dot data is itself less than L. L is -10, right? So can I say all of its left will also be less than L? So we were returning root dot right. Now what's going to happen? See, you have find out that okay, fine, this -13 is less than your -10. So you are going to return all of its right subtree. That's going to give you a wrong answer. Why? Because this will be removed and you will have -11 to the left of 6, right? That should not be there because if you see -11 is outside the range, right? So is this clear, Vidya, why in order is not working? Similarly, guys, for pre-order, if we go, okay, pre-order is also the same thing in the sense, not exactly same thing, but what you are doing in pre-order, you first do operations on root, then you do operations on left and right, right? Then you do operations left and right. That is also going to give you a wrong answer. You should not do first operations on root. First, you need to fix your left and right. Otherwise, wrong things will get returned. Okay. See over here, if you're trying to do a pre-order, let's say if you're trying to do a pre-order, okay. So here itself, what you're going to do, you are going to check this root dot data, right? This is fine right now, but let me show you where we are going to get the error. This point, -13. You are checking, okay, and let's say this is -11. You are checking this, okay, okay, just a second. Yeah, I can get error over here as well. 6 also, the 6 is in range. See, what I'm saying is when you are at 6, you have not yet checked your left and right, right? So your left and right will have multiple things or multiple values which are not in range. So you should not straight away start doing the operations. You should first fix your left and right subtrees. Okay, like you can do a detailed dry run and you can see, but overview is there is only one traversal that is ensuring me that my left and right subtrees will be fixed in the beginning, then only I should go and process the corresponding parent of it, right? Or if you want, you can do changes in the code and you can see the exact dragons. Okay, guys, is this clear? Vidya, am I able to answer your question? See, I need to show the dry run also. Okay. Okay, great. So thank you for the confirmation, Vidya. So guys, any one of you have any questions, do let me know. Okay. Now let's try to do a dry run. Okay, let's try to do a dry run of this. Like I don't think it's required because I've explained it multiple times, but it's fine for the sake of completion. Okay, let's do it. So what we are going to do is, okay, let me redraw the tree over here. Okay. So what was the tree? Initially I had six. Okay, just a second. We have the color. So initially I had six. Let me go back to that screen. Six. What after that? What do I have? I have just a second. I have minus 13. Don't worry, guys. I'm taking bright color because I need to go there, and that's a dark background. So I have minus 8. I have 13. I have 15. So it will be visible over there properly. 6 minus 13, 14, minus 8, 13, 15, 7. Okay, great. So now let's go there. Okay. 6 minus 13, 6. 6 minus 13, 14, minus 8, 13, 15, 7. Okay, that's correct. Okay, so let's go to this and let's maximize this. So this is your tree, right? Fine. So let me change the color. Let's take orange. Okay. So what we are doing over here, we are initially checking if root is null or not. So that's not the case because you are passed with 6 and this is minus 10 and 13, right? That's what we saw. L and R. Fine. So we are going to again call remove keys because root is not null. It has 6. Basically, see, I am making you visualize with data, but it's not data. It's a node, right? Inside the node, we have, excuse me, we have the key as 6. So we are calling on root dot left. That is calling on this node. Again, we are calling on its root dot left, which is null. So we are over here. Okay, we return. So how are the calls going? 6 minus 13, right? And 6 to the left of 6, I got a null basically, so I return. Now I am calling on the right of 6, so I called this, right? Minus 8, sorry, minus 8. Just a second. So I called for minus 8, right? Again, this minus 8 will go to its left and right, it will give me nulls. Okay. After it gives me nulls, I'm checking over here for these conditions. So where minus 8 is lying? Minus 8 is lying in the range, right? So both of these is going to become false, right? If you have a look, minus 8 less than minus 10, false, right? Minus 8 greater than 13 is also false, right? Okay, so what we are going to do, we are going to simply return root. So we are not doing anything over here, we are going to return root. Where are we returning root? Guys, this is the point where you need to understand. This call gets finished, we are going to return root to this. Basically, minus 13's right. See, from there only you called, right? From there only you called it. So this will have this tree intact. Okay. Now what you do, you have your left and right subtrees of minus 13 fully visited. Now what you need to, check for exact data, which is minus 13. You are going to check for minus 13, right? Great. So if you are checking for minus 13, what's going to happen? Minus 13 over here, if I remove this, just a second. Minus 13 is less than minus 10, so we are going to return root dot right. So what is the root dot right? Root dot right is basically this part. So where are you going to return this? You are going to return this to the call of 6 dot left. Okay. So this is my bad, I'm really sorry. I would have written over here dot left dot right also, but I hope you get it right. So you are going to return it over here. So 6 dot left, what it's going to have, it will not have this anymore. It will directly be aligned with this. Right, just a second. Let me erase it, okay? It will directly be aligned with -8 now. Great. So if that is complete, now it's going to go to the right of 6, right? Basically right subtree of 6. So let's see that. Okay, so let me change the color. Fine. So this 6 dot left is complete, right? 6 dot left is complete. Call on 6 dot right is going to happen. So basically, see, I'm not writing all the things in the stack now. Okay, let it be, because anyways there will be a lot of calls in the stack. Okay, but I'm not writing all the calls now. Let's try to visualize it with the help of tree. So let me just erase it. So you have gone to this part, right? You have gone to this part. 14, again you will be calling for 14 left, then 13 left, that is 7. 7 left, you get a null, you return. 7 right, you get a null, you return. Now you check for 7. So if you check for 7, what's going to happen? 7 is in the range, right? So both of the conditions are going to become false. This is also false, this is also false for 7, right? Great. So if that is the case, what you're going to do? You're going to simply return root. So no modifications over here, right? Where are you going to return this? From where it was called. So it was called from 13 dot left, right? So we are going to return the exact pointer. So this tree is intact till now, right? Now we are going to call on 13 dot right. You find a null. So calls for left and right of 13 is finished. You're going to check for 13. So 13 is still intact, right? Means basically we need to consider. That's the reason we have not used equals to over here, right? There is only less than and greater than. Okay. Only if return root dot right, only if root dot data is less than null, and return root dot left only if root dot data is greater than r. So this will also stay there. We are simply going to return root. So this root dot left basically of 14 will be returned with this. So we have all of this intact. Okay, we have all of this intact. Now comes the interesting part. What do you have? You go visit your right subtree, right? Right subtree of 15. So as soon as you visit your right subtree of 15, 15 again calls on its left, returns null, calls on its right, returns null. Check for 15 happens, and it's going to make your this condition true, right? This 15 is greater than 30. It's going to make this true, right? So what you're going to do, you're going to return root left. So you're going to return this part. Although it's not making difference over here, but I hope you realize why we are returning root dot left, because in the right of 15 all are greater than 15, right? So that will surely be out of range. So I am going to return root dot left. So it returns null, and where it goes to the right of 14. So now this 15 goes removed. Okay, 15 goes removed, and we have over here null. We don't have anything basically. Okay, so let me just get rid of this. So now calls for left and right subtree of 14 is completed. Okay, and now you are going to check for 14. So for 14 also this condition is going to become true, right? For 14 also this condition is going to become true. So you are going to return root dot left. So this time see your root dot left is this one. So where are you going to return? You are going to return to 6 dot right, right? From where there you only call, right? Basically you need to override that. So your 6 dot right now will be overwritten. So you're going to return root dot left. So you're going to return this part, basically 13 and 7. So this will get removed, and there will be a join from here to here. Okay, great. So if I just redraw it, how things are going to be, this will be 6. Just a second. This will be 6. This will be -8. This is going to be 13, and this is going to be 7. Right? This is what you're going to get. So all the values are lying in the range, both -10 and 13 inclusive. Okay, this is your tree finally. So I hope guys this is clear. Okay, great. So that's it for today. We are going to come up with one more question that was asked today in problem of the day in tomorrow's live stream. Okay, so thank you guys. Thank you for joining Geeks for Geeks practice. See you tomorrow. Okay.